So our first challenge question in our lab math comes in our solution preparation section where we're talking about preparing solutions from pure solids and liquids. And just to kind of review and highlight some of the things that we had talked about prior, question 1 here sort of deals about preparing what we'd call maybe single component solutions from pure solids. So we only have one kind of component in solution, and so it's a very basic kind of unit conversion to figure out the mass that you'd need to weigh out. Problem 2 has us begin thinking about multi-component buffers, or multi-component solutions, if you will. And in this case, we've got 3 components that we have, but it's still relatively straightforward that each component only contributes 1 species to solution. How our challenge problem becomes challenging is the fact that we are not only comparing a multi-component solution, but the trick to this is realizing that some of the components actually come from multiple sources. So to just kind of go through and highlight some aspects to this. So again, let's imagine that we've got sort of an IV bag here that we have containing our solutions. We know that we're going to have sodium at a concentration of 130 millimolar. We're going to have chloride at 109 millimolar, lactate at 28 millimolar, potassium at 4 millimolar, and calcium at 1.5 millimolar. Now, this problem also tells us that we need to make the solution using the following species. So again, just to highlight here, we can't go and grab sodium cation off the shelf and chloride anion. These come as salts. And so they tell us that the solutions that we can use are sodium chloride, calcium chloride, sodium lactate, and then potassium chloride. And so one of the inherent things to realize here is that something like sodium, right? Something like sodium here, actually that 130 millimolar has to come from two different sources, two sources here. Chloride actually comes from 3 different sources. And so we can't just say we want 109 millimolar sodium chloride, because yes, that would give us 109 millimolar chloride, but it would also not account for the fact that chloride is going to be coming from these other 2 salts as well. So working through this problem, and I'm going to kind of do a conceptual piece to this first before we actually start doing the calculations, we need to really begin the problem by finding something that's only going to provide 1 component to solution. So basically it's anything but the sodium and the chloride. So again, we could start with the lactate. The sodium lactate only provides lactate. So if we consider this, that means if we want 28 millimolar lactate, we'd need to have 28 millimolar sodium lactate, and that's going to contribute 28 millimolar to our sodium concentration. Another species that's only present once, or in 1 species, is potassium. And so for this situation, we could have potassium chloride that we added at 4 millimolar. Let me just kind of highlight here. This really means we're going to be using 28 millimolar sodium lactate. For this, we really could use 4 millimolar KCl, which is going to give us 4 millimolar potassium as well as 4 millimolar chloride. The only other thing that again is present in only 1 species is calcium. And we know that we need calcium to be at 1.5 millimolar. So if we have 1.5 millimolar calcium chloride, that's going to give us the 1.5 millimolar calcium that we need, but it's also going to give us 3 millimolar of chloride. So if we sort of take stock here of the things that are accounted for, right, we've got our 28 millimolar lactate accounted for. We've got our 4 millimolar potassium that's accounted for, and we've got our 1 millimolar calcium that's accounted for. So right now we need to consider the fact that we've got, let me change colors here just to highlight, we've got sodium 28 millimolar here. So again, sodium's going to be here. And then we've got chloride, chloride is going to be present in 3 species. And so we've got 4 millimolar here, 3 millimolar here. And so the big question is, how much sodium chloride are we going to need? So the easiest piece might be to look at the fact that if we've already got 28 millimolar sodium that's coming from sodium lactate, and we need 130 millimolar total, then the difference must come from sodium chloride. And so that sort of tells us that we need to have 102 millimolar sodium chloride. And just as a check, this 102 plus this 28 gives us the 130 that we need. And let's just check out our chloride. So again, chloride is going to be 102 from the sodium chloride, plus 3 from the calcium chloride is 105, plus 4 from the potassium chloride is going to be the 109 that we need. So now these other two are accounted for by the fact that we've got them coming from multiple components. Once we kind of did this sort of bookkeeping exercise, the rest of the problem actually becomes quite simple. In reality, if I had told you at the beginning what these concentrations were that you'd use of these salts, it would be pretty straightforward. So now I'm just going to go through and do the calculations for the rest of these problems. So let's take the sodium lactate that we started with. So if we know that we need 28 millimolar sodium lactate, so it's 28 millimolar, so it's going to be 28 millimole sodium lactate per liter. We know we're going to be using 1 liter because we want to make 1 liter of this solution. 1 millimole of sodium lactate is 112.06 milligrams of sodium lactate. And do a little unit conversion here. 1,000 milligrams is 1 gram. We get 3.138 grams of sodium lactate. Next one that we figured out was potassium chloride. So going through and doing a similar calculation for that, we know we want 4 millimolar potassium chloride, so 4 millimole per liter, again times our 1 liter. Molecular weight for potassium chloride is 74.55 milligrams of KCl for 1 millimole. Again, taking 1,000 milligrams for a gram to put this into reasonable numbers, we're going to have 0.298 grams of KCl that we've added. Next one that we went through and did was our calcium chloride. So we know we want 1.5 millimolar calcium chloride, so that's 1.5 millimole of calcium chloride per liter. We are making 1 liter, and molecular weight is 110.98 milligrams of calcium chloride. That ends up being 0.166 grams of calcium chloride. And the last one that we actually figured out was the sodium chloride. And again, that was a number that we actually had to do some calculating to figure out that we want 102 millimolar sodium chloride, making 1 liter again of solution using the molecular weight of sodium chloride here. .961 grams of sodium chloride. So for this sample video, I'm not going to go through writing the description as well, but remember our description comes in this Mad Libs form. So basically using an analytical balance, we would weigh out the 4 masses that we determined of those 4 different substances, quantitatively transfer the solute to a 1 liter volumetric flask, add deionized water quantity sufficient to 1,000 milliliters or 1 liter. Again, with this specific problem, it doesn't say anything about pH, so we're not necessarily adjusting to physiological pH in any way, but that is likely what happens here. The last part of the problem, clearly accounting for all concentrations of species in solution, we can kind of see that from this picture that we have here. You also could kind of go through with these concentrations that you have here. Once we figure out this 102 millimolar, then you could sort of figure out the different sources for your chloride and for your sodium ions. So hopefully pretty straightforward once you're walked through it. Again, sometimes these problems just seem so challenging when you first look at them, but hopefully you kind of saw this one as a neat puzzle to work through.